Hello everyone. I'm very happy to share my recent result on Succinct blind quantum computation using random oracle. I'm Jiayu Zhang from Boston University. So what is blind quantum computation? In this problem, Alice has a quantum circuit C, and he wants to evaluate it and get C0. But it doesn't have the ability to apply C itself. So it makes use of a remote quantum solver. But on the other hand, it doesn't trust the solver and want to keep this secret. So it wants to design a protocol to interact with the solver and get the result in the end. This is the fundamental problem in quantum cryptography. The problem itself is very important because with high probability in the near future, quantum computers can only be used as cloud service. So if we want to make use of its power, simultaneously want to keep our data or circuit secure, such a protocol is needed. What's more, the study of this problem has often led to new techniques that can be later applied in related problems, like quantum computation verification, which is a fundamental problem in quantum cryptography. There are three minimum requirements for this problem: quickness, security, and efficiency. For security, we use indistinguishability-based security, which means any malicious server could not distinguish whether the client is using the real circuit C as the input, or is using the zero string as the input. So these are just minimum requirements, and there are still many different settings. In this work, we give a new universal blind quantum computation protocol where the client-side quantum computation is succinct, which means it is at most a fixed polynomial of the security parameter, and is secure in the quantum random oracle model. So let's first give a review of arXiv works, and we'll focus on universal protocols using only a single quantum solver. arXiv works can be classified into two classes. One class is IT-scale protocols, and the representative is a protocol by broadband feasible cryptography. In this protocol, the size of quantum gadgets are prepared by the client is linear to the size of the circuit to be evaluated. Another class of protocols is protocols based on public encryption. An early representative is a protocol by Dulles, Java, and Spielman. And recently, Maha developed a protocol based on linear with error assumption. In this protocol, the client can be completely classical. In this work, we'll focus on assumptions and ask the following question: what if we only have symmetric cryptographic primitives? And later, we'll model symmetric primitives as a random oracle. We also have a specific goal. We want our protocol to be better than the existing IT-scale protocols, which means we want the client-side quantum computation to be independent of the circuit size C. So if we classify protocols based on client-side quantum computation and assumptions, we get the following table. And this table shows different trade-offs between these two factors. And we can see our protocol reveals a new trade-off, where the assumption is the quantum random oracle model, which is an idealized symmetric crypto model. And the client-side quantum computation is succinct, which is between classical and linear. So our work reveals a more complete cryptographic picture for this problem. So in the details, our protocol is as follows. There are two phases. In the first phase, the client will send some quantum gadget to the server, and this gadget can be prepared using only polycard packets. Poly is a fixed polynomial. And in the second phase, the client can become really classical and secure in the quantum random oracle model. So what is a quantum random oracle model? This model is written in this paper as a quantum generalization of the classical random oracle model. In this model, there's oracle, which encodes a random mapping, and other parties can curate this oracle. And this is an ideal model for symmetry key encryption of hash functions. It's a formal setting. We can design protocols and prove the security in this setting. And in practice, we can use a quantum random oracle methodology to instantiate the oracle with hash functions of block cipher and claim the security heuristically. But there do exist some uninstantiable constructions, like the scheme given in these papers. But quantum random oracle and classical random oracle have been extensively studied and provide some only known constructions of many cryptographic protocols. So the remaining talk is organized as follows. We'll first give a top-down overview and a framework for protocol design, and go to the technical details. So our protocol will use gadgets in the following form. The client will hold two different strings as the keys, and the server will hold the superposition of these two strings as a gadget. This is used previously in this paper, etc. So it's not part of our innovation. Our observation is the adversary, holding only the gadget, can only output both keys with negligible norm. This observation can be generalized into weaker cases, which lead to the notion of asset security, which is a basic concept in our paper. The top-down overview of our protocol is as follows. First, the client will prepare some quantum gadgets to the server. And each gadget is of the following form, and the keys are different. Both parties will use some classical interactions to expand the number of gadgets to a large number. And this gadget will have some kind of security. Then they will use some protocols to evaluate the socket security. And this step is called remote gadget preparation, and is further achieved in the following steps. First, we will design weakly secure gadget increasing protocol, then elevate the security to a fully secure one. But this part is the most difficult part, and this part is also not trivial. A very informal illustration is as follows. First, the server will hold some gadget, which is fully secure. And both parties will go through some protocols, and the number of gadgets gets increased, but security becomes weaker. And some later protocols will give us even more gadgets at the cost of even weaker security. And finally, the number of gadgets will get increased, but security becomes fully secure again. Certainly, this is only a very informal illustration, and actually, gadget generation and security amplification are not two separate protocols. What we actually do is to use a weakly secure protocol as sub-protocol to design a fully secure protocol as an upper level protocol. So what we're going to do is to first design a modular framework for protocol design. We'll formalize the notion of remote gadget preparation. We'll define the requirements and security. For security, we'll first define the asset security of a state. And based on this concept, we define the normal security and weak security of our protocol. Then we can use this framework for protocol design. And we need to strike balance between queries, security, etc. when we design each subprotocols. So let's formalize the remote gadget preparation. The query is relatively easier. We say a protocol is an N2L protocol if it transforms an input gadget to L output gadget in the only setting. And we want it to be gadget increasing, which means L over N is bigger than 1. For security, let's first define the security of a state. So this is our state. And the state captures the purified joint state of all the parties. So the green part is also important, but we want to focus on the most basic things. And we say the state is to the eta A as secure for key pair K, which is key pair held by the client. If the following conditions are satisfied, to the eta is upper bound on the current number of the unitaries. If all the servers are unitaries with less than these current numbers, the server could only output both keys in K with norm at most A. Then we say the state is to the eta A is secure for this key, which means the server's ability to output both keys using this number of queries is upper bounded. Then based on this notion, we can define the security of our protocols. With a protocol has output security eta, if and only if the output state is 2 to the eta 2 minus eta as secure for each key pair in the output keys. And this is a strong security, and we can see the security is potentially secure. But what we need in the design of each subprotocol is a notion of weak security. And for weak security, the input security is also part of the definition, which gives us better control on the behavior of the protocol. And we say a remote gadget preparation protocol has weak security transfer parameter eta c to p or eta prime c prime. If the following statements are satisfied, here eta and c captures the security of the input, which is defined in terms of the S security for each input key pair. And P eta prime C prime describes the security of the output key. So for the output part, one of the following conditions need to be satisfied. Either the passive probability is upper bounded by P, or the output has S security for each output key pair described by eta prime C prime. Here, C prime is not necessarily exponentially small. So we can see the security is more general and could be weaker than the normal security. So let's go to the technical details. We'll first construct a weakly secured gadget increasing protocol. Then we'll use an amplification technique called repeat and combine to amplify the security to a fully secure one. So to design a gadget increasing protocol, let's consider the following problem. The goal is to generate 2 gadgets from 1 gadget. And the output gadget could have some possibly weak security. These are quantum mappings. And the idea is to use the reversible lookup tables or reversible upper tables given in this paper. But it's not easy to do that directly, because these reversible lookup tables require the input number to be at least equal to the output number. The key idea here is to introduce a bitwise permutation, which permutes the bit position of these two output gadgets securely. And this permutation is sampled by the client and kept secret from the server. And this will provide some extra protection when we do the reversible encoding in the first step. And finally, the client can review the permutation to allow the server to depermute the output gadget. But this also seems to be a dilemma because, on the one hand, we want the client to keep the permutation secret to preserve the security. But the client eventually need to review it. So we need some idea to solve this problem. What we're going to do is to further introduce a helper gadget. So the mapping in the first step will actually goes as follows. And after we use some way to implement these mappings, the helper gadget will go to some protocols called petty Hammar test. And this subprotocol is a petty variant of the Hammar test in this paper. Simply speaking, what we're going to do is to measure this state in Hammar basis and get a D such that D times A0 equal to D times A1. And as the name suggests, we need to add some paddings in these protocols. And these paddings will allow us to prove some powerful lemmas on this subprotocol. One lemma is called proof unpredictability, which formally says if the server can pass this test with some probability, its ability to predict the keys for the post-test state will be limited. Which means if we consider the whole protocols, we can observe that at each time step, either the permutation or the keys in the helper gadget will be hidden from the adversary's viewpoint. We can see before the petty Hammar test, the permutation is secret. And after the Hammar test, the adversary will lose the ability to compute the keys in the helper gadget. And this is essential when we design the encoding in the first step. And when we design the mapping in the first step, we can use the reversible lookup table. And we can see this is still a mapping from 2 gadget to 3 gadget. But we can first pass one input key pairs for reversibility. And this part is given classically to the server, so the client doesn't need to add any extra quantum computation for that. But this is still not enough for to get a protocol that is secure on both of the output gadget. And we need to do more. What we need to do is to observe that the reversibly encoded part has multiple ways of it. Actually has multiple possible reversible encoding. And we will choose 2 different reversible encoding and associate them to different components or branches of the helper gadget. And we'll make use of the property that the overall reversible encoding will behave differently on these 2 branches of the helper gadget, and use it together with the proof untestability property for the petty Hammar test. to guarantee the security. And we can get some more intuitions from the for this protocol. One way is to consider a attacker which is semi-classical. And we can see if we omit the permutations, even a semi-classical adversary can break many rows in the table by decrypting back and forth. In this way, I get an intuition of how the permutation protects security. Another viewpoint is Petty-Harman test viewpoint. And we can see there are two branches of the helper gadget. And the behavior of the over reversible encoding behave differently on these two branches. And what the adversary can do on these two branches are actually different. But they do have an intersection, which is honest mapping. What's more, the properties from the Petty-Harman test force the adversary to behave somewhat coherently on these two branches, which in the end implies that informally and intuitively, what the adversary can do could not be too far away from the honest mapping. And the formal proof of weak security take a Petty-Harman test viewpoint and technically merge intuition from the classic adversary viewpoint. So this way, we get a protocol that is weakly secure, but still not gadget increasing. Because although we have created one more gadget from the reversibly encoded part, we can assume one for the helper gadget. The final observation is we do a parallel repetition of this subprotocol, and the helper gadget can be shared. And we can get a protocol that is both gadget increasing and still weakly secure. So now we get a weakly secure protocols, and we can go to the application. And the application technique is called the repeat and combine technique. Let's first go to the source of weakness in the definition of weak security transfer parameter. And we can focus on the output part. And there are two cases for the output part. One case is the Python space is bounded by some probabilities. And in this case, we have no idea how the output will behave. And P can be close to 1. Also, the gap is inverse polynomial. I want to first get rid of this case by using a technique called the repeat technique. And secondly, in the second case, C prime is not necessarily exponentially small. We want it to be exponentially small by using a technique called combine technique. In the repeat technique, what we are going to do is mainly a parallel repetition of the subprotocols. And after, and we require the server to pass the test in each of these subprotocols. And this will improve the security. And the security of the upper level protocols will be better than the security of the inner protocols. But it's still not sufficient to give us exponentially secure protocols. To make it exponentially secure, we need to use a technique called combine technique. It's basically written as follows. Let's imagine initially the server will hold some will hold two weakly secure protocols. And the client will instruct the server to measure the XOR of the subscripts. And this will collapse these two gadgets into a single bigger gadget. And the client can compute the combined keys from the measurement result. Intuitively, in dream world, if the server wants to break the security of the output gadget, it has to have the ability to break the security of both of the input gadgets, which intuitively means the security of the output gadgets could be the multiplication of the security of the input gadget. And if that's true, we can combine many gadgets together, and the security of the final gadget will be exponentially small. But that's not true actually, and there's no free lunch. The problem is these two different gadgets can be correlated, and their security can also be correlated. So we need to do more. What we're going to do is to carefully design the time order of gadget generation and security amplification. We don't want to generate many gadgets altogether and combine them. We want to design the order of these two steps more carefully. And what's more, we'll use a layer called security reflection layer. This will help us decorrelate different keys. So our structure of combining is actually as follows. We take the subprotocols that come from our repeat technique. We don't want to apply these protocols on each block altogether in parallel. We want to apply them on each block one by one. But every time we apply them on a new block, we combine them to the old gadget. And after these combinations, we go to the post-repeat subprotocols on a new block and combine them. This will provide some decorrelation, but that's still not enough. So what we're going to do is to use a new layer called security reflection layer. And the properties from the security reflection layer will help us decorrelate these keys and guarantee the output keys will be exponentially secure. And this layer will consume some small number of virtually secure gadgets, but it can strengthen the security for each of the input keys. Let's first consider the following problem to understand the security reflection. Let's imagine initially the server has some gadget, and this gadget, the security of this gadget is guaranteed by the secrecy of a key K. But what if K is protected securely now, but is made insecure by some later protocols? So we want to introduce some virtually secure gadget and switch to base the security of this gadget on these new keys. So let's first try to understand the basic routine. So here x0 plus x1 is the initial gadget, and x0 plus r1 is a virtually secure gadget. And the client will send a lookup table, which encodes YB and XB RB prime. So each key in the initial gadget corresponds to the same key in the output gadget, but correspond to the corresponding keys in the output gadget, but different keys in the fully secure gadget correspond to the same key in the output gadget. And after the server completes this decryption, the new gadget is thrown to the Bendy-Harman test, so it's consumed and being tested. And after this protocol completes, the security of the output gadget will also rely on the secrecy of the new gadget in a weaker form. And this will give us some kind of security, even if the keys in K is revealed later. Certainly, it's still weak security. but we can amplify it to a fully secure protocol. And this subprotocol can refer to security for many input gadgets. And to make it exponentially secure, we only need to use polycappa 30 secure gadget. So we can use some small number gadget to refer the security on many input gadget. And the proof is actually trivial and technical, which is given in the paper. So in this way, we can get a exponentially secure protocol. But there's still a final problem. The combined technique seems to consume too many gadgets because the combined technique combines couple gadgets together. But the weakest secure protocol, given the first half, only allows us to asymptotically double the number of gadgets. But this can be solved. We can first subcompose the weak secure protocols to boost the gadget expansion ratio from 2 to tilde kappa. And on the other hand, in the combined technique, we can reduce the gadget number down to square root kappa. The overall protocol will be both gadget increasing and fully secure. And now we can give a glimpse of the security proof technique. First, we need a framework. In a state level, for the security, we use the most basic part is the S security. And we also need to use some other kind of security. And we need a way to describe the well-behavedness of the states. For example, we don't want to study states like the XOR or the random error contents. Formally speaking, we want the state to be able to be prepared using a bounded linear sum of states of a limited number of random error qubits. And on the protocol level, we make use of the definition of the weak security transfer parameter. And sometimes we also need to generalize this definition. And for the lemma, one important lemma that we need to use is the state decomposition lemmas for the quantum random oracle model. One example is as follows. So these lemmas will serve as a bridge from weak security to full security in this paper. In my opinion, these are some general lemmas for quantum random oracle model, so they are possibly useful in other places. We know that the upper-level ideal state decomposition also appears in some other works, but these are still very different lemmas and very different techniques. And the proof that applications in our settings are quite different. Formally speaking, we can prove that any weakly secure state in the quantum random oracle model can be written as the sum of an exponentially secure state and the bounded norm state. So these two states are not necessarily orthogonal, but such a decomposition always exists. And we also need to require both states have some reasonable level of well-behavedness relative to the original state. And this requires some trivial proofs using an iterated convergent decomposition. So this way, we get a secure remote gadget pre-registration protocol. Now we can go from the remote gadget pre-registration to the universal block quantum computation. The notion that we will use is a gadget exceeding 8 basic factory. Each basic factory transforms this superposition gadget to the single qubit gadget. The single qubit gadget will become the building block of BFK protocol. Because the setting is different from the setting from the original Q factory paper, so this step is not a simple application of the previous works. But simply speaking, what we're going to do is to first use some non-collection basis test step to get some verifiability on the input part. But if we assume the input is honest, what we're going to do is to use the phase table to encode the phase gate securely. And in this table, we can allow the server to add a phase in this superstition gadget and use the Hama measurement from this paper to collapse this state to a single qubit state. Finally, we can run BFK protocol to complete this construction. Summary, we get a protocol where the client uses only polycopper quantum gates and secure in the quantum random oracle model. Which reveals a new trade-off between classical quantum computation assumptions. And there are some open questions in this table. There are still many unknown cells in this table, and my understanding for these unknown cells will be very interesting. In the top left corner, although we already have some negative evidences, we still want some deeper understanding for that. Thank you for listening.